I'll give you the following cheat sheet on this quiz. Conservation of mass, rho dV plus integral ds cv rho u dot n hat dA is equal to 0. That's conservation of mass. And I'll also give you this one. Conservation of linear momentum. Where the only difference between these two is that basically you're tracking this quantity rho here, and here you're tracking this quantity rho u. The momentum, this is momentum per unit volume here. Okay, and this is the flux of momentum per unit volume into the system. And this F, as you remember from, we did these problems with these carts on wheels. This F designates how much total forces are acting on this thing to keep this thing stationary. So what forces are acting on this thing to keep it stationary? And that includes not just whatever bolts are on this pipe, but also any kind of other forces. So it's the sum of all forces on the device to keep it stationary. All right. And this is for a stationary control volume. At the end of the lecture, after I do two problems involving conservation of momentum, I guess somebody just turned the computer on. We're going to talk about moving control volumes, which I said will be a very minor part of the quiz. If you really can master the use of these two equations, you'll do quite well. Basically, if you've got a moving control volume, the only thing that changes is this is for moving control volume. The only thing that has changed is our flux term has to be considered relative to the control volume. Your flux always depends on basically what the control volume is experiencing. We talked about these problems. Imagine like you're an ant on the surface of the control volume. The amount of fluid that's coming in depends on the relative speed. Okay, where W has the usual definition, U minus UCV. There's one last version. So part of the reason I do not put the moving control volumes as a major part of the quiz, because there is some, I would say, a lack of clarity in the book. There's basically, they use the following version. So this is for a moving control volume with an inlet and outlet that's moving with where there's basically no addition of fluid to the control volume. So this is a moving CV with fluid entering and leaving. So, for example, not the rocket problem. It would be, I'll give an example. For example, we have this moving plate that we'll do in a few minutes. So there are basically 4 different versions. You'll really be responsible for these first 2. There might be a minor one on these last 2. But those are really like going to be a minor part of the quiz.
Professor?
Yeah?
Question. So now I don't have finished the homework, but pretty much a lot of the problems that we have, we get to cancel that first part of the equation because it's steady state.
That's correct. So, yeah, most of the problems in this course are going to be steady state from now until the final. So yeah, you're right. You basically do not consider these 2. The only time we did consider this first term was, I I was going to say filling the bathtub. Filling the bathtub where basically the height of the tub increases. But you're right, there's very few problems that I've assigned for homework and that are given that involve these first two terms. One example that would involve this maybe is emptying a container or filling a container, and I think, but otherwise, it's a minor part.
Okay, so we're mainly like, what would clue us into making sure we include that part would be a change in volume or a change.
Yeah, things are actually changing with time. Anytime someone draws a steady picture and nothing's accumulating, it's going to be steady state. You can ignore these first two terms. Any other questions on? So I'll give you these on the quiz. And remember, W is equal to. So basically, this means if the control volume is not moving, W is equal to U. Okay. All right. So this is a pipe elbow. Gravity's going downward. And so just like the problems that we did for class yesterday, anytime you make fluid change direction, you're going to get a force. Ideally, like because of Newton's law, the fluid wants to keep on going the same direction, but anytime you change its direction, you're going to get a force. And you can consider this kind of acting like a rocket. Fluid's going in, and then basically you're directing it towards this way. So you're going to have some component that's going to push it in the opposite direction, right? Basically, it's actually shooting out fluid from the bottom left. Now all we have to do is be precise and incorporate the fact that fluid's entering here and leaving here, and the fact that the diameters are different. It's a common principle among all these problems that you're going to have to use conservation of mass and linear momentum. For example, in this problem, they do not give you U1 or U2. They only give you a Q. But if you want to figure out the secondary velocity, you just know that there's nothing accumulating. Use constant. The other thing they give you is the two pressures. So these two pressures, it'll be the first time we incorporate pressures. In the cart problems that we did last time with basically blowing through these cones, those were free jets. So we didn't really consider pressure in those cases. But this is, whenever they have this weird symbol here, it means that the pipe just keeps on going. So it's not like the pipe ends there. It's actually just going, and then you're considering fluid inside the pipe. So like peeking into the pipe. Okay. So because the pipe is a metal pipe, it can retain pressures. We got to be able to consider those. All right, so in this problem, drawing the control volume is quite straightforward because there's really not that many options. The only thing you want to be careful of is that, remember, all these integrals have outward normal to the control volume. So when you draw it, just make sure that it's normal to those fluid velocities. Right? So we're going to have n hat here. And now define our axes, x and y. So there's normals everywhere on this control volume, but the ones that we care about are the ones at the inlet and the outlet. So n is equal to negative x hat. We'll define this one in a second because this one will be a little more complicated. And let's write what the vectors are. So blue jeans, folks, I just added the control volume in red. All right. U1 x hat, right? Now, I want you to see if you can figure out what U2 is in terms of theta. And then you can figure out what n is, and then you'll be able to figure out the whole thing.
Dr. Hu, could you go back to that first one for just 1 second?
Here, I'll leave it there while you guys do this. So and see if, think what happens when theta is equal to 0. We'll have to do this trick again for the next problem.
For the outlet of the control volume, would we say it's equal, n hat would equal negative y hat? Or what did you say for that?
It's going to be a combination of x hat and y hat, depending on what theta is.
Oh, okay.
You'll involve cosine and sine. Good. And when you're done with that, you can write the conservation of momentum. So this problem also, we can just, to use conservation of mass right now. Rho, no, there's no rho. Because that's already flow rate. U1 pi d1 squared over 4 is equal to U2 pi d2 squared over 4. So by this definition, you can just use U1 and U2 everywhere. You could propagate them through, but in this case, it's easier to substitute at the very end. All right. So the key thing to realize is x and y are to the right and up. This vector u2 is to the bottom and to the left. So you're going to have negative signs. Okay? All right. And you can test this out. For example, consider when theta is equal to 0, then it's completely in the negative x hat direction, right? And in this case, just n hat is going to be in the same direction. Okay, so now that's conservation of linear momentum. Again, there's nothing accumulating. Let's just start rho u, and this pipe thing is not moving. Let's start with the left-hand side because we've already done that. All right, so we've got to consider the inlet and the outlet. There's only two places where you have a u that's actually pointing in the normal direction. Okay. So we got rho u1. We can just write the vector rho u1, and then here n hat is going in the opposite direction as an inlet. So we got negative u1 times. We'll call this a1, where a1 is equal to pi d1 squared over 4. A2 is equal to pi d2 squared over 4. Okay. Plus, again, we have rho u2. N dot u2 is just going to be magnitude u2 because it's an inlet. There's no negative sign. Oh, sorry, it's an outlet. Okay, so this is a vector equation. You know, you've got an x component in this side and an x and y component here. Now, this is a pretty key part that I think some people on the quiz may forget because it seems like it's optional. And that is that you've got to include the pressures of the fluid because this is all enclosed inside the pipe. And the direction of those pressures are always defined into the volume, into the control volume, because that's what we call positive pressures. We don't like positive pressure because it's like crushing us. So, for example, remember from hydrostatics, we learned that pressure does not have a direction. It exerts equally in all directions. But once you've defined these two control surfaces, you do have a direction. So it would be P1A1, P1A1 times x hat, all right, it going inward. And then now we have this one. This one's also going inward, because they're both positive pressures, P2, plus P2A2. This is just going to have to be messy, necessarily, plus sine theta y hat. This direction denotes upward to the right. Okay. Plus whatever else. In this problem, so this is 5.34. I should have written there. They had the weight of the elbow plus minus weight elbow times y hat. And then minus your anchoring force. All right. And so that's pretty much the entire problem. Where you have basically these are pressure terms. Weight of elbow. That was given in the problem. And then now you have this last term here to make sure that it balances. Because there's no guarantee, the left-hand side is all because of the fluid. Same with this pressure. But the only way you can actually keep it stationary is if you have the adequate anchoring force that makes sure that equality holds. And because you've got momentum in the x direction and in the y direction, you're going to have both momentum in the x and y.
Could you explain why the forces on the control surfaces are equal and opposite? Or, well, not equal and opposite, but like just opposite to one another?
Oh, you mean, right? You're asking why these are two different signs?
No, like I saw this in the book too, but like when you drew the pressures P1A1, why are they both pointing into the
because
control volume?
Because they're positive pressures. We define positive as always going into the control volume. If they're negative pressures, they would both be going out. So it is very different from the momentum problem. The momentum problem, we actually cared about, the direction of the fluid velocity. But it doesn't matter if you got fluid coming in or out, as long as it's got positive pressure. You control, basically, your control volume, if it ends there, that is the pressure that's exerted on it.
So these forces are with respect to the end direction. So that's what makes it positive.
Yeah, because they're only there where the fluid is. Like basically here, this is like a bunch of asbestos or whatever, like pipe fittings. There's no fluid out here. Same with here. They only exist where you've got fluid. From Bernoulli's equation, anytime you got a flow, anytime you got speed, you're going to have pressures.
Right.
The way to imagine is, so you have this pipe fitting and this fluid going through. Imagine you just took that pipe fitting out and replaced it with a block of ice, just momentarily. You just took it out and put a block of ice there. Well, basically, just the pressures alone would send that block flying to the upper right. Just the fact that fluid has a positive pressure at both those ends.
Okay.
Thank you. That's the way you think about it. And if you go back to statics, I think they have a similar definition for when you look at forces. Yeah.
For the left-hand side, do we do out minus in, or is it just we isolate each instance and look at the n hat, or
Okay, this is a good question. Becca asked this question. So you don't. There's going to always be an outlet and inlet, but if you start thinking one's positive, one's negative, you're going to sort of double count. the negative signs arise naturally from the fact that it's an inlet and an outlet. So here, just because n hat is opposite u hat, you got a negative. Here, n hat is with u hat because it's outlet, you get a positive. And that's what brings about these negative and positive signs. If you start thinking, oh, well, this is positive and this is going to be negative, you're going to have a negative sign here, and that'll be really bad. It's always basically, this integral just means adding. You're adding the different portions. I mean, we could have just written this as a sum, really, but the fluid dynamicists, they like to do math. So. But basically, yeah, this is across the whole surface, and there's basically just two regions of interest. This one region and this two region. Everything else, like n hat exists everywhere else, but u hat is 0 over there. So you basically don't get a contribution. But yeah, they're going to pertain to basically inlets and outlets. That's the only way fluids can provide forces that you care about. If it's going tangential to control volume, there's no forces. So we care about inlets and outlets. You guys okay? So make sure you do include the pressure forces. No, I got to say it one more time because I know someone's going to miss it on the quiz because it's not given in the equations of motion. It's something you have to think about physically of what are the forces acting on the right-hand side. And this is the only one that we're going to be practicing with the pressures. The next one's a free jet.
How do you know when to incorporate the pressure terms? Because like on some of the homework problems, I would think to include the pressure, but then
it depends on the situation. Here, it's like an infinitely long metal pipe, and you're basically just cutting the pipe off because they're putting the fittings there. If this were, so we're going to do this next problem when you do not have the pressure terms because it's there's no pipe. If there's no pipe enclosing it, there's no way to contain pressures. So let's just do that problem now. And that's a little bit more involved in this one because you have to use conservation of mass. All right. So hopefully you're not getting, it's not that scary, the integrals, because we don't actually use like the full power. The full power of the integrals. No, we don't use them. We just basically just like, make them into products.
Dr. Hu,
Yeah?
why do the anchoring force terms show up as negative?
Just because I think in the solution they have it facing.
Just the way they drew it.
Yeah.
Okay.
It really doesn't. Basically, if you make it positive, you're going to have. It'll just change the way your convention is. So,
Okay.
So that's because of they just drew. So that's not really that critical. But you should just keep in mind, whatever's remaining on that right-hand side is necessary to balance the equation. All right. So this problem was 5.34 in my version of the book. This next one is 5.57. Oh, this is a nice problem. I did this on a test once. I did this on the final exam one year. All right, so you got fluid. Oh, why did I erase that screen? Okay, it doesn't even work anymore. Was that ever lowered, this lecture?
Not today.
Okay. Oops. Oh, no. All right, we just have to wait. Because it's left and right, and I have no idea if it's facing me or away from me. U1. Oh no, this is going to be called UJ. UJ. So this is like if you're trying to throw a frisbee into a gardening hose for some reason. This is what would happen. 5.57. All right, so that's DJ for the D diameter, U2, U3, theta, F anchoring. All right, all right. And we'll make this even a little bit easier. I'll call this AJ. So we'll have the areas. So as you know from the previous problem, if you know the diameters, you know the areas. So you can sort of label them in the beginning and reduce your algebra later. A2, A3. All right. Okay, so this problem asks three things. Okay, so given uj is equal to 40 meters per second, aj is 30 millimeters squared. All right, and they say the velocity magnitude remains constant as air flows through the plate. Okay, so the first thing we got to find is okay. The all right. So there are three parts to this problem, and after we do this, I think I'll reinforce this. We'll do this one more with a moving cart of how to approach these type of problems. So this first one, you just got to calculate how much momentum is coming in and how much is leaving those directions. You're going to have to use this fact, and you're going to have to use conservation of mass to figure out the areas and the velocities. So that's the big issue. You know the input velocity and area, but you don't really know the two outputs. Then this is a sort of, A and B are kind of very similar. You've got to really figure out the fraction of mass flow going in 2 versus 3 in order to calculate A. And this one, last one is, imagine this, you're throwing the Frisbee into the garden hose, and the Frisbee gets pushed by the garden hose at this speed. And this last one, physically, we're going to see this over again in conservation of angular momentum. Whenever you allow your system to be pushed, you're going to have a resultingly lower force. All these problems, for example, that pipe problem, if we allow this pipe to be moving to the upper right, you're going to get a lower anchoring force because you're letting some of the momentum carry you. All right. All right, now the key thing in this problem, and I think I gave this as a hint on the final exam one year, is that the best way to do it is not with the typical axes x and y, horizontal and vertical. The best way to do it is like this. X, y. Okay. Oh, that's super non-clear. And we define all our variables in terms of that. The reason for doing this is that if you keep it horizontal and vertical, all of your terms are going to have cosine and sine, and that's just inconvenient. when you do it this way, you only absorb all the cosine inside one of these terms. And x and y are arbitrary. As long as when you solve for force, it's basically using that coordinate system. So you want to use a coordinate system that makes your life easiest. All right, so conservation in this case. Let's define the variables first. So with that coordinate system, so number one, so use x, y. Use x hat parallel to plate to reduce trig. All right, and with that definition, we have our variables. So uj, I'll let you see if you can write the trig for uj and u2 and u3, and then we're going to start contribution mass on the next side. And then you can start doing the anchoring force. You actually don't even need to consider U2 and U3 for the anchoring force, because they've defined the anchoring force perpendicular to the plate. All right. So you really just want to check so basically, uj is going to the right. That gives you some component in positive x and some component in negative y, right? Because y is actually going that way. So, so some component in positive x and some component in negative y. And to check it, again, assume theta is equal to 0, where nothing's basically, you're not going to have any component perpendicular to the plate. And the nice thing about the way we write the coordinate system, u2 is now just positive x hat direction, 3 negative u3 x hat direction. So you could solve the problem with a different coordinate system, but it would make this problem less convenient. Okay. All right, now let's do part A, the anchoring force. And the way we've drawn it, the anchoring, basically, let me just show you, point to this again. These two fluids, they are basically not provide any contribution to FA, because anchoring force is defined perpendicular to plate. In this problem, they might have said there's no shear forces, but basically, you only get contributions of momentum if you've got some component that's parallel to this direction that we care about. And these are all perpendicular in the wrong direction. So the anchoring force, let's just write this. rho u dot n hat dA is equal to sum of the forces. Okay. All right. And this anchoring, what they call it Fy, this anchoring force. The only contribution you're going to get is the component due to the in the y direction. So anchoring force negative rho, and the negative from the uj, so we got rho uj squared. Basically, you have fluid coming in, push, push the plate back towards the fluid. So, to remind you, basically, from what we learned from dimensional analysis, rho times the velocity squared, that gives you a pressure. Pressure times area, that gives you the force. And the sign theta is because you only used part of the you only use part of the uj. The rest of the uj is pushing it to the right, but this is the only part that's actually pushing it in the board in this direction. All right, so that's part A. You guys okay with part A? Okay. Now for part B, the fraction of mass flow. There's a certain the integral form basically equates to this, that there's no inlets in that, there's no accumulation of mass, and the inlet is m dot j, and the outlet is m dot 2 plus m dot 3, where this unit means a mass per time. Okay. In terms of the variables given, you got this, U2, A2, U2, A2 plus U3, A3. Now, just like we saw for a Bernoulli equation, every time you introduce a new sort of entry, inlet and outlet, you're going to introduce new friends to the party. Here you've got these two areas which you don't know. The only way you can solve for them is by using the fact that's given in the problem, that the velocity magnitude remains constant. So you got uj is equal to u2 is equal to u3. Okay. And if you have that, you can show that aj is equal to a2 plus a3. Okay. So now so this is all conservation of mass. Now, we haven't used the x component of conservation of linear momentum. Now, use x hat component.
Actually, I think the computers are below.
Oh, yeah, thanks. All right, time to go to board 1. Let's leave it there so people can copy it. No, just erase.
Dr. Hu, I have a quick question.
Go ahead.
So why is AJ equal to A2 plus A3?
If you assume that these are all constant, you can cancel them.
Okay, gotcha.
Imagine just dividing everything by uj. It means that, I mean, I think that's probably an experimental fact. They probably test that experimentally. I actually haven't done this problem in real life, like in built-ins. So I don't. Does anyone know what conditions would lead to basically velocity magnitude remaining constant? Yeah?
An incredibly small, like infinitesimally small area of the plate.
A small area. Oh, you mean small AJ or just a small plate?
A small plate.
Yeah, I think that would help. Definitely, you would only. So we haven't covered this yet, but when we do this thing called the energy equation, the velocities can actually decrease because of what viscous effects. Like for example, you have pipe fluid going through a pipe. It doesn't flow through forever. It's always going to slow down. So if the plate's really small, you're going to have very little, and if the plate's really smooth, you could have very little viscous effects, and basically the velocity wouldn't change very much. That is a course project begging to happen. All right. So where were we? Okay, so the x component. So we use the y component of the momentum equation. Let's use the x component of momentum. Because there's no anchoring force in the x direction, so those are necessarily going to have to balance. So the x component of the momentum equation gives us this. Negative uj squared cosine theta aj is equal to negative u3 squared a3 plus u2 squared a2, where I've gotten rid of all the rows. And I moved one of them to the left side.
Can I ask?
Yeah.
You get cosine, like when you got cosine and sine, I was
Yeah.
a little bit confused because it seems like you dot cosine with negative cosine because like the outward normal would be the same thing with just magnitude of 1, right?
So for this problem, here, let's go to this board so people can actually understand what we're talking about. All right. Anytime you've got the velocity vector going in one of these directions, we've always designated that n hat's going to be just parallel to it or opposite. So here, in this case, does this have anything left? No.
So the idea is you just dot it together.
Yeah. N hat.
Same thing as a negative thing.
Yeah. N hat is basically always going to just be in the same direction or opposite this direction. So in that case, for that n hat is going to be negative cosine theta plus sine theta. Oh, no, get it messed up. Minus sine. So it shouldn't be anything, it should basically be the opposite direction of that, that's all. And when you basically dot these two, it's basically a vector dotted by it's basically a vector dotted by itself. But if you really wanted to get pedantic about it, like for example, so n hat dot n hat is just going to be 1, right? But that also arises from the fact that cosine squared plus sine squared is 1. But you don't. But basically, you're always going to either consider this dot n hat, and you're either going to minus sign if it's inlet, and then plus sign if it's outlet. Does that help? All right, where were we? Board 1. Okay. All right, so this is the remaining components of that equation. And then cosine theta aj is equal to negative a3. So again, the uj is equal to u2s. Okay, so this tells you how the areas change. The relationship between the first area and the second and third one. And you combine this with the previous equation that we had, aj is equal to a2 plus a3. These are independent facts. The first bottom one was from conservation of mass. This is from conservation of the x component of conservation of mass. So you can combine them and you can show a2 is equal to 1 minus cosine theta over 2 aj. a3 is equal to 1 plus cosine theta over 2 aj. Okay. You got two unknowns, a2 and a3, and you got two equations. So that's enough to solve for it. So this is part B. And anytime you're looking for that second equation, it's either going to be conservation of mass, conservation of linear momentum. And keep in mind, conservation of linear momentum really has two equations. It's basically got the x component and the y component. And here you're basically assuming that there's got zero forces in the x direction. That the fluid jets and the momentum contained therein basically balance out themselves. All right. So for part C, we have to get into what happens when sort of the nozzle is outside the control volume. And then after this, maybe we should do talk about the homework. It's dragging along. So, oops.
Dr. Hu, you moved us along to slide 3. Could you go back to 2?
Yeah, sure. Oh, sorry. I'll call this a lemma. The book kind of just glosses over it, but basically that's true for this situation where you've got a control volume that everything in is coming out, and the nozzle's on the outside. So the reason why that's true, so in general, so let's just ignore the steady state term. So if it's steady state, we only have to consider the second term. And remember let's just keep it rho in front. This is the flux, which is volume per time. And this is the linear momentum, so momentum per volume. Okay, so this is defined in the lab frame, and this is basically changing if your control volume has a different speed. Now, if you use this definition, U minus UCV, you can also rewrite this, and we will do this again for the conservation of angular momentum. All I'm doing is rearranging this. This says that the relative velocity is defined as whatever velocity is in the absolute frame minus how quickly your control volume is going. And this is just saying, well, I can write the absolute velocity as how quickly I'm moving relative to the control volume plus the control volume speed. Right, they're saying the same thing. And if you substitute this in, those are some of your forces, and we split it up, well, you can write this term as UCV rho W dot N dA is equal to, so just plus this. Because the fact that UCV doesn't depend on any of the inlets and outlets, doesn't depend on the relative velocity, so we can pull it out. And because this whole thing, everything going in is coming out, by conservation of masses is 0. So this whole thing, you lose this whole thing. Okay? And you're just remaining with the left-hand side. So in general, we have this term, this equation, but for the particular case that everything going in is coming out, you just have that left-hand side. And that's the version we're going to use for this problem. All right. Let's just do that on. Yeah, let's just use this third board. Erase first. This last part of the problem, we consider this thing moving to the right. And physically, we should get a lower force because we're letting some of it be carried. All right. So we need to use this equation. So we're given that it's moving to the right. So physically, I don't know. So now this thing is going to the right at UCV. We're still having this UJ. Okay. So the sum of the forces okay. Now W is equal to U minus UCV. So if we really we got UJ, which I'm just copying what we had before, x hat minus sine theta y hat minus UCV at minus sine theta y hat. All right. UJ minus UCV. Right. This is a complicated way of saying that sorry, my picture got messed up. UJ and UCV are both going in the same direction. This funny direction that I've incorporated with these trig symbols, but ultimately it means this fluid that's hitting the plate is lower. The relative velocity is lower because the plate is moving to the right. Conversely, if I was mentioning that UFC fighter championships, if you run into the fluid, you're gonna have a higher velocity. But you're lucky, you're running away from the fluid, so you got a lower velocity. So, this is gonna give you rho uj minus UCV squared sine theta aj. Okay. This is, like I said, the moving control line is going to be minor or not even on the quiz. But it is a substantial part of the book, and people were very confused before without that lemma thing. Okay, so we got 15 minutes. Do you want to talk about the homework? Anyone raise your hand if you started the homework. Any problems that you want to discuss briefly?
Could you go over 5.59?
Yeah. All right. So 5.59 involves this sluice gate. Sluice or sluice? Is it like juice?
Like juice.
Sluice. Ooh. I'm going to drink some juice. All right. Sluice. All right. So you got this thing, this gate that closes. And they want to compare the force required to hold it when it's in that position and was it closed. Well, my intuition is that it should be a lot more force when it's closed, but the question is how much. And so this is 5. You said 5.59, right?
Yeah.
All right. Okay. So we'll call that H. We'll just call it H because there's only one height in the problem. So this thing wants to be like a guillotine to the water and chop it, and water's going to go down. And they actually drew it really physically correct because, I mean, it does have some forward momentum. Therefore, it doesn't just go that way. So it does go down like this. And they tell you this sort of equilibrium height. They call it little h. Right? And they also tell you that this thing's not only just holding water, but it's also holding back like a river. Okay. All right. Magnitude to hold it there and closed. So the way they want to compare the following problems. This problem to this problem, where basically it's exactly the same thing, except now this thing is closed. All right. So let's draw the control volumes in both cases. Now, so the reason I went all the way up to the right here, because I didn't want to include these weird curvature effects. You don't want to include anything that you don't know the dimensions of. That's the big thing. Because I don't know how well it's curved, so let's go all the way till I know the height h, little h. And this other one is straightforward. So what matters in these control volume diagrams is like other problems, is the areas of the inlets and the outlets. So you've got to make sure those are perpendicular to the normal, basically parallel to the fluids, and that they're, we just got to make sure they're parallel to the velocities, and they are. What doesn't matter is the width of this control volume. That doesn't matter, because all we care about is the anchoring force, so the vertical force. Sorry, the horizontal force. So we care about this force, F. X, Y, Fx. Fx. So we don't care about the width of this thing. If you make this thing wider, it just means you got more vertical force. The weight of that fluid supported by, all the forces down here. But because this gate is perpendicular to those vectors, this is all we care about. All right. So let's do the easy one first here. So this one gives a blast back to hydrostatics. Rho G. Fx is equal to hydrostatic pressure, so P n hat dA. Here the n hat vectors are all going to be in the x hat direction, so we'll just call this F in general. F. And the Fx, we're going to get, so remember P, these are all the pressures. P. And the other thing, when it's closed, you have no fluid velocities. So actually become this, you definitely want to do the right-hand side first. This is the easier one. So rho G Z, from Z is equal to 0, Z is equal to capital H, rho GZ of W dZ. This has units of pressure. This has units of area. Pressure. And we'll get our usual result, which is 1/2 h squared. Right? Those hydrostatics keeps on coming back. Okay. All right. So if you did quiz 2, this right-hand side should be okay for you, where W is equal to width into the page. And that's only the X forces. The Y forces, I mean, clearly there's like this, the ocean floor has got to do stuff. It's supporting the weight of the thing, but we don't care about that. Okay. All right, everyone okay with the right-hand side? Those of you taking the final exam, you have to beat these bad puppies later.
Does the h squared come from the yeah, what
Z.
is
Integral of z dz is 1/2 z squared.
my bad. Okay.
Yeah. Good question. All right, now we got to do this part. All right, so there's 2 issues. The fact that you got fluid coming in here, and then you got fluid exiting. 2 things. They're going to have different heights, and they're going to have different velocities because of conservation of mass. So let's use conservation of mass, which says U, W, H is equal to whatever U2 is, WH. So U2 is going to equal to U times H over H. In other words, it's like a nozzle. You're squeezing that fluid out, it's going to have a higher velocity. All right. Now, okay, so now we got the magnitude U2. Now we got to use conservation, this conservation problem. So we got rho U hat dot n hat dA is equal to the sum of the anchoring forces. All right. The left-hand side, so U is equal to U x hat, U2 is equal to U2 x hat. Okay, and we can use those magnitudes later. So we got rho U, U dot n hat, that's going to be magnitude U. Oh, sorry. N hat, magnitude negative U. Negative U times H times W plus rho U2 U dot n hat. That's going to be positive U2 little h times W. And we have the Fx, the anchoring force of the gate, plus what? Yeah. So you still have hydrostatic pressures. Hydrostatic pressures are a funny thing. Even when they're not static, they're still there. So you got basically, I mean, we've solved for up here, rho g h 1/2 h squared. So you have whatever was on the left minus the fact that you basically, I mean, basically if you do these little hydrostatic pressures down here, you have minus rho g w. I gotta be a little careful. Let's just do it for real up here. And they're always, those two, that positive sign is because it's going, hydrostatic pressures are going into the page this way. And let's just draw a little miniature version. Board 2. All right. All right. There's a P1 and that's P2. All right, so let's see. The hydrostatic from force 2, I'm just going to be a little careful. Fx, I'll call that Fx2 is equal to Z is equal to, so we call this Z equals 0, and then we call this Z is equal to H minus H. All right. and we call this z is equal to h. So it's from z equals to h minus h of rho g z w dz. Rho g w 1/2 h squared minus h squared. All right, so basically, I don't want to write. So because of that, this whole thing, rho g w 1/2 h squared minus 1/2 rho g w h squared plus 1/2 rho g w h. I'm sure there's like a smart way to do this and not do this pedantic way. We get this, but yeah, just like people said. So you basically have that hydrostatic component. I guess physically, you can think of it. I mean, if you really wanted to avoid all that math, you could have just looked. You could just look at the board and say, hey, when I have this flowing, it's basically these two parts are going to cancel. These two parts are equal and opposite because remember Pascal's law says pressures are equal along horizontal lines. So I don't have to. I can just ignore those, and only on the left is that. And I can just integrate between little h minus h at 0. All right. 5 minutes left. Any other questions on the homework? Or is this one okay? I think the big thing is that people forget to use the pressures, the hydrostatic pressures. But anytime you got fluid that's in a control volume and there's gravity, you're going to have hydrostatic pressures. Better to include and say you included it than to ignore. I mean, this is also, technically speaking, they did not say gravity is important, but it's a sluice gate, so it's like a big amount of water. It's like a physical thing. The river's held down by gravity, so it's 10 feet tall, so you got to account for the gravity. Any other requests for jukebox homework time? Any other questions?
Dr. Hu?
Yep.
I have a quick question for one of the homework problems, and then would you be able to go over another problem, please?
In 5 minutes, we'll do what we can, but we'll definitely do
Okay.
it in office hours, whatever we don't get. Go ahead.
Okay, sounds good. So then, can you just do 5.63 if you can, please?
All right, so 5.63 gets to some radial polar coordinates here. All right. And we'll probably just continue office hours on this board because the class after this is totally, I don't know, they just got moved. 5.63. All right, so we will see this problem again later. Okay, so this is going to be a kind of bad rendition, but it's supposed to be coming out of the board. Ooh. Yeah, that's supposed to be coming at you. All right. So fluid's coming in and it's spraying out, but only in the half plane. Oh, that's bad. So it's in the half plane, that tells you immediately there's going to be a force, because fluid doesn't like to be sprayed out just in the half plane. Right? They give you this R, all right, and they give you this, the jet velocity at the exit, they give you this uj, okay, and they give you this height, h. All right. All right. So we've got fluid velocities going everywhere in this half plane. So you can denote one of the, like the one that I drew here arbitrarily, call that theta. All right. So uj is coming out of theta, and we've got to integrate. But this is the first time you actually use that integration symbol. So rho u dot n hat dA ds. So in this problem, I'm going to try to keep this control volume. Basically, you know, n hat's going to vary over along the thing, but it's always going to be in the same direction as uj. So we call, okay, uj, okay, so u, I'm going to say it's in, just in the, how are we going to do this? Well, okay, if this were the, let's do a really top view, all that. I don't really like the way they did it here. That way. X, y. So if we have x and y, u theta is going to have some component in the negative y and some component in positive x. So, and when theta is 0, it's all in the x. So cosine theta x hat u theta. Right? So when theta is 0, it's all in the x hat direction and nothing in the y. And otherwise, according to the picture, where theta is going to vary between 0 it's going to go between theta is 0 and negative pi. That's not super convenient, but that's what we're just going to do. All right, so we got rho. Okay, 9:15. So if you got to go, you can go. I'll stay here and do this problem for office hours. We'll probably just do office hours here. Kyung-deok is going to do the 6 to 8 or 8 to 10. 8. We'll start at 8, right? People say he's very helpful. So come see Kyung-deok tomorrow night at 8. Shell tutoring. Still, anyone do shell tutoring? Anyone check out this Blue Jean shell tutoring? No one needs it? Did people go when they were in real person?
I've had a couple friends go, and then they would go, and the people wouldn't be there.
Oh, people wouldn't be there?
Yeah, that was last semester.
Oh, okay. It should be better this semester. This we will do conservation of, basically these conservation equations, we'll do them for 2 whole quizzes. This quiz and next quiz, except next quiz is going to be angular momentum and energy. I consider next quiz to actually be a little bit easier because there's only one type of problem. But this one, you got to get the vectors right and stuff like that. So, and if you need me, let me know basically as soon as possible today of what time on Tuesday you'd want to do it. Then I'm happy to do something. I'll also say, I haven't taken the averages, but I would say people who take the quiz in class, I would say they're, on average, probably doing a little bit better. Just because you don't have to, you have basically 5 minutes more time, you don't have to copy the things. So if you want to take it in person, make sure you sign up by noon today. Okay, so class dismissed, but I will hang out. Let's take a 1-minute break and we'll hang out and do these problems for, who is that, Sunny? Are you asking this question, Sunny?
Vishwa.
Oh, Vishwa, okay. I'll do this problem for Vishwa and whoever wants to stick around. Let's take a 1-minute break. Got here taking time. Yes. If you need your quizzes, it's okay. Yeah. So do you need to modify number 2 or anything? Okay. Okay. But I think it looks. They're a little bit. I think they're fine. It's nice problems. Very nice problems. So you get send that today. I'll send to the guy before 1 today. I'll just get it out. And then Wednesday you don't have, unless you want a proctor, and that'd be abusing you. So you can just relax on Wednesday. But I'm glad you got it early this week. It's like super stressful if we do it at the last minute. Easy problems become hard problems when you have like no time. All right. See ya. Okay. Okay. I'm just curious, who's left on Eugene's world? We've got 7 people left. I know. Okay. All right, Vishva. All right, let's see. So I've defined theta, and it's going between 0 and negative pi. And I've defined uj. So now I've just got to add all that stuff up. All right, so integral, and this is mostly across the area. So there's going to be theta is equal to 0 to theta is equal to negative pi. Not super. Rho of the vector uj, I'm just going to copy it. Now let's just substitute in, because we're going to actually have to evaluate this whole thing. Reacting magnitude uj cosine theta x hat minus sine theta y hat. U dot n. Well, lucky for us, we've chosen n to be the same direction as uj. So that's just going to be magnitude uj. Times dA, which in this case is h d theta, times r. h r d theta. So where in the world does that h r d theta come from? Imagine it's like this thing. It's a little pie wedge. Pumpkin pie. Like on sale recently. Pumpkin. D theta h. Like a thin slice of pumpkin pie. Just like that. Okay. And it's got a height h. It's got a perimeter length of r d theta when theta's in radians. Okay. All right. Now we just crank this through. And rho uj squared times integral of cosine theta x hat minus sine theta y hat. Yep.
The HRD theta, why are we getting a volume instead of an area? Yeah, shouldn't it just be RD theta?
RD theta has units of length, and H has units of length. D theta, funny thing, I don't know around quiz 1, but theta is actually no unitless. Radians are like this funny world. You can't it's not a length unless you know the radius. So this is still, yeah, good question. Theta is equal to 0, theta is equal to negative pi. All right, and d theta. All right. So rho uj squared hr. Negative sine theta x hat minus cosine theta y hat. Rho uj squared hr. The y's should be canceling. Sorry, no. The x's should be canceling because they're equal and opposite. I'm pretty sure that's the case. And the y's should be like double or something like that. yeah, sine of pi is the same as sine of 0, so that's good. Minus cosine negative pi minus cosine of 0. Cosine of negative pi, that's like negative 1, right? And cosine of 0 is 1. So negative 1 minus 1 is equal to negative 2. And then negative 2 times 2. So this is equal to 2 rho u d squared. So no x force. So no x force and only y forces. And it's, of course, if they were spraying out radially everywhere, it should be like equal y force. It should be, they should all cancel. But because it's only coming through one, it doesn't cancel. Oh, the monitor.
On the quiz, is it okay if we do separate equations for each component?
Oh yeah, whatever will help you not mess up. I think people do not like it when I combine the components, and they don't like it when I use vector notation, right?
Well, vectors are fine. It's combining the.
Oh, like this?
I'm gonna get so lost.
Oh, the reason I personally do it is because the prefactors are going to be the same, so you save yourself a little bit of writing. And you just got to keep in mind that the conservation of momentum, that's actually two equations. But anytime you could recognize similarities, I think you'd reduce errors. That's just me. Everyone should do it their way.
Hey,
Vishwa, are you satisfied?
Yes. So I just have a few more, I guess, smaller questions pertaining to a few of the problems. Okay.
Yep.
So on 5.54, with the tank and the dish,
5.54.
for
Yep.
finding F2, when doing the vectors for U3, they use two different velocities. They use the previously found velocity and the newly found velocity from Bernoulli's, and I'm not sure why they use different velocities.
Because it leaves the tank at one speed, and then it accelerates by gravity, and it hits the thing at another speed. So the exit velocity of the top tank is not equal to the entrance velocity of the bottom tank, because it's actually fallen a distance of 12 feet.
Yep, I understand that, but in the equation for finding F2, the anchoring force for the dish, they use both of those for the U3 calculation in the conservation of linear momentum.
Oh, okay. The reason they use both of those is because, see ya. The reason they use both of those is one of them dictates the rate of flux, and the other one dictates how much momentum it has. So the rate of flux, this m dot, is given by the lower velocity, but how much momentum it has is given by the second velocity.
Okay, so the u vector, they use the top velocity, and the u dot n vector, they use the bottom velocity.
The other way around. The higher velocity is basically how much momentum it has. The lower velocity is how much flux it has. So when you're asking how much flux, you're asking how much volume per time is coming in. Well, it's given by the area times whatever's leaving, the top one, right? Because the top one has basically, it's got some volume per time leaving. So you have that much volume per time coming in, but then how much momentum that has is given by the new velocity, the higher velocity.
Okay, so the flux term is u dot n.
The flux term is u dot n, and it's the lower of the two velocities, yeah.
And the lower velocity.
Yeah.
and the momentum term is with just u, and that's why they use the higher velocity.
Yeah. So I think you're going to get the same. I think you're going to get the same.
Sorry?
Yeah, I think you're going to get the same thing if you even use switch that. But yeah, the correct one is you do the lower velocity for u dot.
Okay.
So Dan, you come in person for the office hours.
Yeah. Well, I wanted to go over the last quiz.
Oh, okay. I don't have. Oh, I have them up here. If you. Oh no, but you did yours electronically.
Yeah, I have mine.
Oh, okay.
I was just,
Yeah, I guess it's a lot easier to get up at 9:30, get out of bed at 9:30 than at 8.
yeah, I'd rather just do it from my room.
Okay, Vishwa. So do you want me to do that one? Do you want me to draw it on the board and explain it further, or you think you got it? Oh, the other people here. Do you guys get 5.54?
Yeah.
Yes, you want me to draw it, or you get it?
I'm all set.
Oh, you're all set. Okay. So Vishwa, you're all set.
Can you you don't need to draw it, but can you just one more time explain why each term uses that velocity?
Let me just draw it. This is like a. Whenever I do the hours right after class, it feels like those telethons. Like they ask for money, and you still have to keep on going. I'm probably going to run out of energy in about 10 minutes, but we can do it until then. Okay. All right, so we got this thing. So do you want to know what this T1 is first? Then it's leaving. Is anyone else on blue jeans except for Vishva?
There's one more person.
Okay.
I am
Who's that?
Sarah.
Sarah what?
Dominguez.
Oh, Dominguez, okay. And you want to talk to me about your quiz project too, I think.
Yes.
All right. Did you want to do that after class today?
I guess. I mean, I think Xander's there in person too. I think.
Oh yeah. Oh, that'll be perfect then. Oh, but Daniel, that means you'll have to wait even longer to get your to the quiz, because I want them to leave first because they got 2 people. All right. A1. All right. So they say, what is the tension T supporting the tank? What is the force F2 to support the dish? All right. All right. So part A. And let's see. They do include the weight. So they have this is T1 minus W1 y hat. So we only consider vertical forces. We only care about y. All right. And this one, we got rho U1 y hat. So yeah, I'm going to just label it. U1 is equal to negative U1 y hat. And we're going to show that's negative rho GH H1. What's the velocity from Bernoulli? It says E is plus 1/2 rho U squared is equal to constant. Rho GH. Rho GH. Rho GH. Plus 1 constant. So U is equal to root of 2GH. negative square root of 2gh y hat. And the issue with u2 is that it keeps on falling. So this is going to be negative square root of 2gh1 plus h2, right? Y hat. All right, so you got basically one speed here because of falling to height h1, and then another speed because of falling h1 plus h2, okay? Where this is u2. All right, so for the part A, you have that equation, and u dot n is just u1, magnitude u1 n hat times a1, right? Equal to that stuff. But for part B, the problem is it's got a higher speed. So you got rho u2, the amount of momentum it has, but the flux is not at that higher speed. The flux is still from conservation of mass. We got u u1 times a is equal to the sum of the forces. This is basically the volume per time that's coming in. So that's why they use that. So it's basically each of the fluid velocities has this vector, has this amount of momentum, but basically the amount of fluid that's coming in is given by this one. Does that make sense?
Yes.
I would say that's actually a little bit tricky because we usually use the same use for both.
Yep, that was the difficult part of this problem.
But I think
Because originally I just put all the velocities as u.
Yeah, but that would kind of be overcounting it. Like if you had u2, let's say you considered u2a here. That's basically like there's more. You're assuming there's more fluid than there actually is, but there's only the amount of fluid volume per time is only given by u1 times a. So it's a little bit different. Like usually all these jet problems, we have a jet coming in, but here it's a jet that has a higher speed than the amount that's coming in.
Okay.
And if you wanted, you could do this problem two ways. You could also do it a way that you include this control volume, and the fact that you have accumulating, you basically have that is actually a reservoir momentum too. I think that might account for the difference because it's basically accelerating in that time that it drops at height.
Dr. Who?
Yeah.
I just have one more conceptual question.
Okay.
If that's okay.
Yeah.
Okay. So sometimes when I was doing the homework problems, I was having trouble conceptualizing or visualizing the direction of the anchoring force. So in problem 5.40 and 5.45, would you mind just kind of walking me through how you can visualize which direction the anchoring force is going in? Just so the signs I use are correct on for the quiz.
Say the problem number again.
5.40 and 5.45.
Oh, I don't actually have this printed.
Oh, sorry, 5.40 is not on the homework, but neither of those are on the homework. Oh, those are just extra problems I did.
Oh.
Okay.
You might have to do these back in my office because I don't have the.
Okay.
But
no worries.
Ultimately, it doesn't matter. You don't need to know the direction of the anchoring force because it's good. The sign of all the momentum steps are going to dictate what the anchoring force is. Like for example, this one, I didn't have to know that T1 was up. The difference between the left-hand side and the right-hand side will dictate what T is. You could just choose one and make sure that the direction that I've drawn T1 is the same as I have here, and then either they'll be positive or negative in magnitude depending on how good your guess was. You shouldn't need to really know the direction.
Okay, so just assume everything is positive, and then the n hats will allow the signs to change.
Yeah, you assume it. basically, eigenforce is defined as whatever is required to keep this equation as equality. So it'll tell you what it needs to be.
Okay, cool.
But it's good you're doing extra problems.
Yep. Thank you. I think that's all from me. Thank you so much.
Oh yeah, no problem. Okay, now, okay, let's go with